CERN 70 at IIT Madras. We are celebrating 70 years of CERN, fostering the spirit of scientific and collaboration and innovation. This event, before we start, I would like to invite our esteemed guests to the dais. Before we start the event, Professor Manu Santanam, Dean ICSR IIT Madras. Please. Sri Sunil Ganjuji, Secretary AEC and Head DAE. Unfortunately, he is not able to join physically, but he is on the Zoom. Please switch on the Zoom. Next. Charlotte Lindbergh Orakule, Director of International Relations, CERN. Please come to the dais. Dr. Gaurav Agarwal from DST, please come to the dais. Professor Gauthier, spokesperson CMS collaboration, please. Professor Kanjilal, former Director IUAC, Chairman India CERN Task Force, please come to the dais. Professor Vedanga Mahanti, Deputy Spokesperson, Alice Collaboration, CERN. Please. Before we start, we'd like to invite our distinguished guest for a lamp lighting ceremony. Please. Here. No.
Persist. Now it's there.
Gaurav,
We can do it again.
together. I would like to request esteemed guests to take their chair. Please. As a token of our appreciation for their presence and contribution, we would like now to present banquet and memento to our esteemed guests. May I request Professor Manu Santanam, Dean, IIT Madras, kindly do the honor. So, Sunil Ganjuji, so we'll send you banquet offline.
Thank you very much. Well received.
Thank you, sir. Charlotte Limbo, please. Professor Gautier. Professor Bedanga Das Mohanty. Professor Kanjilal. Dr. Gaurav Agarwal. Once again, we extend our heartfelt gratitude to all our esteemed guests. Before we start, I would like to invite to speak few words Ganjuji. Please.
Yeah. Thank you very much, Professor Behra.
Thank you.
It is indeed an honor to be here, although unfortunately I could not join you in person. I am missing the sweet company of all the dignitaries on the dais in person. My good friend Charlotte is there, I can see, and our other colleagues from the LS CMS collaboration are here. I am really very glad that the CERN 70 celebration is part of the IIT Madras event. In fact, it's a matter of a great coincidence that the Department of Atomic Energy is also celebrating its 70 years this year. We are into the 70th year celebration. CERN also was founded in 1954, and the Department of Atomic Energy was also established in 1954. So it's a great coincidence, and I think this association, it just starts from that founding year, but our collaboration and our interaction has been as old as this founding days. I recall the Indian collaboration with CERN started somewhere in 1960s when the Tata Institute of Fundamental Research started interacting with our colleagues at CERN. And since then, it's been a long journey and a really exciting and a very fruitful journey. I'm sure all of you will be hearing about it over the during the discussions in the meeting today. What draws me much more closer to the facts here is that we started in 1960 with a small group collaboration, and today, after all these years, we have the associate membership at CERN. It has been a long path, which did take a lot of efforts on both the sides in terms of science, in terms of physics, if I say, and the scientists and researchers in the Indian research fraternity and even in the CERN fraternity have been working hand in hand for a long time. It's been a very vibrant and a very, very productive collaboration all these years. I think there is one more aspect, or maybe one more significant point which I'd like to highlight here, because right now we are in IIT Madras celebrating this event. There is a statue of Lord Nataraja which was gifted to CERN, I think somewhere in 2004. It's almost 20 years now. And that sculpture itself is a testament to the skills which are abundant in this side of the country. It is a very unique structure and a very unique sculpture which combined art with science. And then it is actually a very good display at the CERN laboratory. Many of our colleagues, many of the people present in the audience might have seen that. And whenever I get a chance to go to CERN, I do make it a point to get a picture clicked along with the Nataraja. I'm also reminded of a famous saying by Carl Sagan when he equated the Nataraja statue, because Nataraja is a form of Lord Shiva in the Hindu mythology, and he is known to perform a cosmic dance. In the similar way, the research objectives of CERN are linked to, in a way, the cosmic dance of subatomic particles. That's what CERN has been doing all through these decades, having the largest particle collider, the Large Hadron Collider, which is a 27-kilometer long collider. And a lot of great things have come out of CERN. Many of the people, or maybe all of the people in the audience will know that CERN is the mother to the World Wide Web. And it is this technology today which is helping me to be able to be joining you all in a virtual mode. And I must congratulate IIT for that. The network here is pretty strong. I'm having no glitches also for that. CERN has many other credits to its discoveries. I think you will be hearing about it. There is a lot of student faculty here, and I think these young minds will need to know how science has progressed within the CERN community and within the Indian community. A lot of big applications for particle accelerators have come in. We have, to a major credit, the God particle and the ghost particle. Both have been discoveries at CERN. I think many of my younger colleagues will like to know about it more. The God particle refers to the discovery of the boson, and the ghost particle refers to the discovery of neutrino. So they have contributed to the fundamental understanding of our universe, and we have made a long stride in our quest for the mysteries which evolve the origins of the universe. Besides that, CERN technologies, when they pursue the excellence of science in very high-tech and cutting-edge technologies, these technologies have also been used or are getting used in societal applications. For example, one of the crystals which was developed for the CERN experiments is now an essential part of the PET scanners which are used worldwide for cancer diagnostics. Similarly, we have the hadron therapy machines, the electron radiotherapy machines, which are all, in a way, offshoots or spin-offs from the technologies which have been progressing and developed at facilities like CERN. It's indeed been a great experience being associated with CERN from our side, from the Department of Atomic Energy. And I think I must right now maybe stop here, because otherwise I will take up all the speaking space for the other speakers who I'm sure have much more to say and to say much more in details today. I'll be unfortunately missing the discussions and the presentations, but I wish this event all the grand success. And I'm sure all the young minds, the learning minds here, which we also call the inspired minds perhaps, they will benefit from these educational and outreach programs, and it will inspire them to pursue science to a much higher level of perfection, excellence, and inquisitiveness. Thank you very much, Prafullaji, for making all these arrangements, and I'm indeed grateful for that. With this, I thank you all. Thank you very much.
Thank you, Ganjuji, for your history of Indian association with CERN, which I was not aware of also. And it's enlightening to know that how we are involved in this journey from the beginning. Thank you. Thank you. I would like to invite Professor Kanjilal to say a few words on this occasion. Use this mic, no?
Good afternoon. I feel very happy to be present. I am audible? Yes. So, the CERN, in simple language, is a great place on earth for scientists, engineers.
It's not audible.
It is not. It is not coming. Sound is not coming.
Mic is on green. It is
It's coming.
on.
Sound is not coming.
Yes, yes.
There?
Yeah.
Okay. Fine. So, for scientists, engineer alike, till you go to CERN, you can go to the internet for the young students particularly, see almost everything in science and technology, engineering we talk about, we learn about, is explained in various ways. It is one of the best websites I see around. And in accelerator is the largest accelerator, and it is a place scientists from all over the world work together. It is for all nations, all countries. And I am from basically accelerator field, lot of ideas, beam dynamics, beam optics, even numerical techniques, physics, ultra-high vacuum technology, anything we need. Accelerator encompasses practically everything. One of the field which encompasses all fields of science and technology, engineering. So it is there. You will learn about CERN from the CERN people. That will be better. I am not talking much about that direction, what it is doing. One thing I can tell, basic idea which all the scientists gets attracted to CERN is understanding the building block of nature to the finer and finer and finer level. And that is great. So it is going on, understanding fundamental particles, seeing them, experimentally observing them, understanding the essence of that, requirements of that to build this universe is very important, and people are doing. That is very good. As a physicist, I really like. And I see a lot of young minds, they start working with CERN collaborations, and today they are stalwarts in the field of physics or science, or some of them in engineering, and all over, in India, abroad. So everywhere they are there. from India, from various countries. In task force, I have come here for as task force. Our main aim is that to best utilize the facility, and it is supported, this all your activities, by Department of Atomic Physics and Department of Science and Technology equally. So that is also great, and it comes under Mega Science program, collaborative program, and we look forward to support this collaboration to keep happening, and we support more and more real research activities, development activities together with CERN. Thank you.
Thank you, Professor Kanjilalji, for your views on this, how the collaboration is evolving and what CERN can provide us as a young mind to grow. Thank you. I would like to invite Dr. Gaurav ji to say a few words.
Thank you, Dr. Behra, for giving me an opportunity to say something from DST point of view. So as we are aware that CERN is a 70-year-old organization, and Indian scientists and other engineers and everybody has been started participating since long. But initially there was a small facility before LSC came up in the year 2004 or something, and Indian contributions are dating back to the construction of LSC through different components. The Mune chamber and jacks and some other items were started from DAE and DST. And with a small projects coming from DST also for electron-positron collider way back before start of LSC were also there. It was after LSC became functional, this mega science project came into a bigger way, and this DAE DST collaboration started in 2006 through a MOU between DAE and DST, and which started basically for the CERN projects but was extended to a number of mega science projects. And after that, this mega science scheme was also formulated, which took this collaboration to newer heights. In the initial years, we had few 4 or 5 groups from DAE and 4 or 5 groups from rest of the country, which were basically funded by DST in that times. Today, our Indian scientists or researchers are participating in 2 big experiments, CMS and ALICE. So as on today, we have 15 active research groups from DST funded institutions and also similar number from the ALICE. Starting from 4 or 5 at the initial times. So this size of the Indian scientific community has grown in the years to come. And in 2016, we started the process of India becoming 2015, we submitted a proposal to CERN for becoming associate membership. So we formulated the proposal, and the CERN task force came to India to evaluate India's candidature for that consideration. And finally, in 2016, India became an associate member of CERN. And from 2017, we are now associate member state of CERN. And now with this higher engagement, Indian industries are also able to participate in a big way in tenders and other things and gain scientifically and technologically. In these years, our CMS and ALICE activity has also grown up across the country in different institutions and new labs. This is on continuous support between DAE and DST through their long-standing MOU, and this has been continuing so far. We are grateful to DAE for their continuous support to us, and the research groups, they have been continuously participating in different activities at CERN in these 2 experiments. In fact, these 2 experiments, Indian participation in these 2 experiments is taking care of a number of aspects from DST point of view. Basically, it's human resource development. Large number of research to PhD students and postdocs are participating in these 2 experiments. This is one human resource development point of view. Second is technology development. R&D, because we are regularly upgrading different components like muon chambers and other detectors. So Indian groups are engaged in continuous R&D, which upon successful completion of the R&D and different P-type, N-type and other items, so they are manufactured or prototyped in the country with the help of Indian industries. A number of Indian industries are also gained. Micropack is one industry in Bangalore which have gained for this, and their expertise and competence building has not enabled not only the India's CERN activities but also to other mega science projects like 30-meter telescope. So this is technology development is also forefront of this collaboration. Human resource development is also there, and international collaboration is also there. So we are also collaborating between the labs, industries, almost all sort of activities are there. And of course, CERN is a place where all science, type of sciences and engineering is coming into picture. Because though it looks that CMS and ALICE are basically physics experiments, but they are using engineering of electronics engineering, computational engineering, data science, and also they require a very different management skills, because different people from different countries and with different subject areas are coming together to achieve a aim. Ultimate they have a aim which is common in nature. So this collaboration is also enabled us to gain a lot of things. So with this, I will leave this place, and I'll request the organizers to invite other speakers. Thank you so much.
Thank you, Gaurav ji, for your insight into how the funding agency works and how it helps to grow the community and how it dissipates this information to the larger community. Thank you. Now I would like to invite Dr. Manu Santanam to give the words about the welcoming the guest and start the function.
Thank you, Prafulla. On behalf of the director and all the faculty members of IIT Madras, I'd like to welcome all of you to this very important and fairly unique event as far as IIT Madras is concerned, to celebrate 70 years of CERN. And I was also happy to note that it's also the 70 years of the DAE. So it's really wonderful that both these events have actually coincided very nicely and have come to IIT Madras. I also extend a very warm welcome to our guests from CERN and from DST and DAE who are here to share their experience with all of you, especially the bright young minds who are here to listen to them and who are trying to aspire to do something in physics and in other branches of science that is quite different and unique as compared to the others. Of course, with IIT Madras, we've had a long history of collaboration with CERN and several other institutions that have led to a lot of innovations in the research that we actually do at IIT Madras. One aspect that we have increasingly been doing is increasing our outreach with respect to how we reach out to members in the scientific community from various parts of the country. There's a lot of work that IITM is also doing in rural parts of India, where we have set up rural interaction centers, where a lot more of the kids can actually get some access to quality education that typically is only confined to cities. So a lot of initiatives have been undertaken by IITM. On the research front, we've been increasingly going to a translational kind of a research. But at the same time, we have not forgotten that fundamental science research is absolutely important, because that's essentially the building block of what leads to more innovations that can lead to an improvement in the quality of life, an improvement in the way that we actually live on this earth, and to ensure that we are able to maximize our use of the resources that are already here. Today, of course, sustainability is on the lips of every engineer, on the lips of every scientist. This is we need to obviously do a lot more than just lip service. Sustainability is something that we all need to practice, need to bring it into the kind of technologies that we create, because ultimately, if we don't use our resources well enough today, we'll have very little to go with in the future. our future generations, many of whom are here, will really bear the brunt of our lack of understanding of this aspect in today's day and age. It's very important that we pay a lot of attention to making the world a lot more habitable, to reduce the impact of the issues that we are facing today with global warming and several other natural calamities that are likely to happen because of these conditions that we have created, man-made conditions that we have created. Why I'm saying all this is because all of these aspects together are linked to the way that we understand how nature works. All of these are also linked to the way that we understand how life came into being. And much of that is the kind of work that is being done at CERN. I had a wonderful opportunity to actually visit CERN in November 2023. I almost felt like a school child because I had only heard about CERN and seen it referred to in books and in movies and all that. It really was a wonderful experience to go and see the labs there, to go and see the experiments that are being done at CMS and Alice, and to see the humongous facilities that are being created just by scientific cooperation and collaboration between different countries. It's just amazing to see what people can do together when they come together and create such wonderful works of science. One more aspect, as Dr. Gaurav was pointing out previously, is that CERN is not just a place where physics is practiced, it's a place where all branches of science and engineering come into play. The creation of those kinds of facilities obviously needs a lot more effort from the engineering community, especially the civil, mechanical, electrical engineers, to try and get things to a condition where these experiments can be conducted successfully. A lot of infrastructure actually gets created, and you'll be amazed to see the kind of work that is happening there. What struck me most, obviously, was the fact that you could find a bunch of scientists sitting together on any given table, and you'll see that not more than 2 of them are from the same country. That's the best part, international scientific collaboration and cooperation that actually happens at CERN. So all of these things are absolutely important in the way that we actually build our future, because unless we move together, it's not easy for any individual nation to actually solve the problems of the entire world. We have to come together as a scientific community, not just in one subject of science, but across the different realms of different types of engineering and science combined together and solve the problems that we actually face in the world today, so we can make the world a better place to live in the future. Thank you all very much for coming here in such large numbers. I'm sure that you'll be enthralled by the kind of stuff that we are going to be seeing from our guests from CERN. The kind of experiments that are being conducted, what are their long-term implications, and how they'll actually go about improving the quality of life as we know today. Thank you very much, and I hope you enjoy the session today. Thank you.
Thank you, Dr. Manu, for your warm welcome to the guest as well as the audience. With this, we will move to the next session, the presentation session. So I would request a guest to just move, and we can clean this space for the presentation session. We'll invite you. We'll invite you.
Okay, go down.
Yeah. So I would like to request Dr. Ipsita to take over the session, and she's going to introduce the speaker and then the interaction session.
Okay, so this is here,
Yeah.
but I think this should be just used as a pointer.
Hi, good evening, everyone. It's a pleasure being a part of this event today, and it's my great pleasure to introduce our esteemed first speaker for today, Charlotte Lindberg Warakaule. Charlotte has been serving as the Director for International Relations at CERN since 2016, where she has made significant strides in strengthening CERN's global partnerships and outreach. As the first person to hold this position, Charlotte has played a pivotal role in expanding CERN's engagement with its member, associate, and non-member states. She has led two remarkable initiatives, CERN Alumni Program and the CERN Science Gateway Project, both of which have had a profound impact on CERN's global connections and scientific collaborations. Before joining CERN, Charlotte worked at United Nations office at Geneva, where she held various key roles, including Chief of Political Affairs and Partnership Building. In these roles, she helped facilitate new multi-stakeholder initiatives such as the Geneva Peace Talks and the Geneva Peace Week. In addition to her work at the UN, Charlotte has contributed to academic research, serving as a Carlsberg Foundation Visiting Research Fellow at Lucy Cavendish College, University of Cambridge, where she also served as the editor-in-chief of the Cambridge Review of International Affairs. She is also a respected member of several international advisory committees and boards, further highlighting her commitment to shaping global dialogue and cooperation. We are incredibly fortunate to have Charlotte with us today. So please join me in welcoming Charlotte Lindberg Warakaule.
Thank you so much. Thank you so much for the very warm welcome. Do you hear me well? Yes, it's okay. First of all, thank you so much to the organizers for the kind invitation to be here. Thank you for the initiative to celebrate CERN's 70th anniversary here at IIT Madras. Thank you so much to the leadership of IIT Madras for the strong partnership with CERN, for your support. Thank you so much also to the conveners of the event. Without you, this would not have been possible. And you are, of course, also strong friends and colleagues of CERN. And we're particularly pleased also to have representatives of DAE and DST with us today, because, of course, they represent the government of India that has been such a strong partner with CERN for many decades now, and particularly now with India as an associate member state. So I really appreciate your very strong words here in the opening. And you have all done my work both easier and more difficult, because you have spoken so well about CERN that it's almost difficult to repeat that. At the same time, you have also paved the way for some of the things that I will say, so hopefully I will not necessarily be repeating, but I will be able to expand a little bit on what we have heard already from the very esteemed speakers that went before me. So now let me see if I can make the technology work, because I have to use the arrows for the slides. I will speak specifically about 70 years of international collaboration and the impact of what CERN does in science on society. Just a quick reminder, we already heard this from the previous speaker. CERN is the world's biggest laboratory for particle physics, and our modest objective is to understand the most fundamental particles and the laws of the universe. And you see here a nice outline of, let's see if this works, yes? Our flagship accelerator, the Large Hadron Collider that you heard, about 27 kilometers in circumference. This is an aerial view. It's 100 meters underground, straddling the border between Switzerland and France. And you will have very nice talks after me from my colleagues with the CMS and the ALICE experiments, if I could make the pointer work. No, it doesn't really work very well. But you will hear in much more detail about the science and what we do. There are 4 pillars that underpin our work. First and foremost, fundamental research in particle physics. This is research that is undertaken and carried forward by a very extensive and very sophisticated international collaboration. This To answer the big questions in physics, we need to innovate. Fundamental research is a driver of innovation. So CERN, we already heard this very nicely previously, that CERN is a big technology lab and a big engineering hub. And together, all these dimensions, research, collaboration, technology and innovation, provides an incredibly rich training ground for the next generation of physicists, engineers, IT professionals, and many, many, many other professions. And I think that's why it's so encouraging to see so many young people here today, because the work we do really needs you to be engaged, and you will be taking this forward for generations to come. So I will speak specifically about the collaboration aspect. I will speak about technology and innovation and the impact of society, and I will speak about education and training, and you will have absolutely fantastic talks that goes much more in detail on the research and on the physics after this. This is an event to mark 70 years of CERN's existence, and also, of course, 70 years we heard of DAE, which is a very nice coincidence. So I'll just speak a little bit about the origins of CERN and how it came about, because that also gives you an understanding of why the structures and the collaboration is the way it is. And you see here a beautiful photo from the 1950s from the groundbreaking ceremony when CERN did not exist, but was being built just outside of Geneva in Switzerland. At its heart, CERN is a peace project and a meeting of excellence in science and peace, and it springs from a very particular historical context in Europe after the end of the Second World War, where there was a coalition of visionary scientists and very forward-looking politicians that were able to bring forward ideas for large-scale, cross-border collaboration in science. Initial ideas brought forward by a very esteemed French physicist, Louis de Broglie. First ideas already 1949, which is incredible. Just 4 years after the end of the Second World War, there are already the first ideas about how to work together across borders in something that had never been attempted before. There was much support also from other regions, and the first formal proposal for creation of what would become CERN actually came from a US physicist, Isidore Rabi, also a Nobel laureate, who proposed to UNESCO, which is an agency within the United Nations, to create regional research laboratories to increase international scientific collaboration. This is the first formal proposal for the creation of CERN. So this was really a vision of peaceful scientific collaboration across borders, and there were three overarching objectives of that vision at the time. First and foremost, to restore scientific excellence, but also to restore that because it was understood that fundamental research in science in general is really a driver of progress. So to rebuild the world after the Second World War, science was really at the heart of this project. There was also an emphasis on fundamental research at a scale that was beyond any single country to take on itself. So an understanding that really big science projects requires collaboration of countries across borders. And then there was an understanding that science can be a glue that can bring people together. Science cannot in and of itself create peace, but it can help to create understanding and bring people together around common objectives that helps to solidify peace over time. So this is really the heart of the project in the early 50s. The official birthday of CERN is the 29th of September 1954. This is when our convention, this is our founding document, entered into force, initially adopted by 12 European countries at the time, and this was the start of a really unique international collaboration in fundamental research, and these are the origins of the organization. So let's look a little bit more about the collaboration that these very visionary founders started at the time. We already heard it. We heard that this is a global community, and we heard very nicely about how in the cafeteria, in the restaurant at CERN, scientists sit side by side, and you will not have two of the same nationality sitting together. And I like this photo, which is from the terrace outside the restaurant at CERN. And not only do we not have scientists of the same nationality sitting together, but we also see that you have young scientists and more distinguished scientists sitting together. This is really a project where you work across borders, where you work across generations as well, which is really extremely encouraging. It's a community today of over 17,000 people of over 110 nationalities. About 13,000 of them are scientific users. They come from universities and institutes from across the world. More than 600 universities and institutes are working in the experiments in the CERN scientific program. So if we look at what the vision of the founders has become today, you can see that the 12 member states have become 24, not just European. We now also have associate member states. We're extremely proud that India is part of that family since 2017. We have a number of observers, traditional big partners in particle physics, prominent among them, the US and Japan. Then we have, and I think this is particularly interesting, we have collaboration agreements with about 50 countries, territories from across the world. And you will see some of them are countries that have more developing communities in particle physics, which testifies to this understanding that fundamental research, particle physics being one of them, is really a driver of progress. And the cooperation agreements we have allow these countries then to develop their capacity also in fundamental research, in particular in particle physics. In terms of the community of about 3,500 colleagues that are employed directly by CERN, they run the infrastructure, but most importantly, we have over 13,000 scientific users. These are the colleagues that come from across the world and work together in the scientific collaborations, and you'll hear much more about that when the colleagues from CMS and ALICE will be speaking to you. And this is really where India has an incredible footprint through the many, many, many colleagues who work in universities and institutes across India. So if we break down this community of users a little bit more, I think that's quite interesting from a collaboration point of view. You can see that about half of the users come from our member states, then a very good proportion from our associate and member states. You can see big community from India and a community that continues to grow, something that we're particularly proud of. Also a good community from our observers. And then about 10% you will see come from the countries with which we have cooperation agreements, again, which shows that this is very much an open lab and it's very much a global lab working with countries and scientists from across the world. I like this plot very much. This shows the evolution of the user community, so these are the 13,000 users, how this has evolved over the past 20 years. And you can see that the global community of users at CERN has actually doubled over the past 20 years. Not just in terms of the number of individual researchers that are working with us, but also in terms of the number of countries that are working with us, which really testifies to how attractive and interesting and cutting edge the science is, because scientists vote with their feet. They go where the science is interesting. And you can see a doubling over 20 years really shows how cutting edge the science is. You can also see that it's connected to the evolution of our projects. Big peak coming with the Large Hadron Collider coming on in 2010, which shows that it's the scientific ambition that really drives the collaboration. You can have ambitions to have collaboration, but you will not have that collaboration unless you have scientific ambition. And it's really the excellence in science that drives the collaboration, which I think is particularly important to highlight. In our collaboration, we work with a core value of open science. And this really shows also the foresight of the founders of the organization. Right after the Second World War, you can see I've quoted the convention that says not only shall the organization have no concern with military requirements, so it's a project of peaceful collaboration in science, but also the results of the experimental and theoretical work shall be made published or otherwise generally available, which means that everything that we develop at CERN, also the technologies, and I'll come back to that in a little bit more detail, that is shared with the world. And this is why you all have the World Wide Web on your phones today. This principle is cascaded through a number of policy documents and initiatives that we have. Open access policy, so this is publishing in open access journals. This is something which is absolutely essential for us. We're very attached to this principle of open access publishing so that everybody can access the results that come out of the scientific work at the lab, and we're very grateful to our member states and associate member states for supporting that because it's so important for our field. We have an open data policy concerning the LHC data, and then all of this comes together in a very innovative open science policy that was promulgated just a couple of years ago that also broadens this to include open source software, hardware, etc. Really, really innovative, and today open science is really the watchword generally in science, and CERN has actually been practicing this for the past 70 years, and we firmly believe that this is part of the success of the lab, the openness and the sharing that comes from that. We also engage on a multilateral level, and of course this is something that's particularly close to my heart. I came from the UN system before I was with CERN, and we can see that we can be a voice also at international level for fact-based, science-driven decision-making. So we engage with international organizations to share what we do, to share our expertise, but also our values such as open science. We have observer status with the United Nations General Assembly, and we work very, very, very hard on promoting also the Sustainable Development Goals. We work actively to see how we can source also technologies. We heard about also the importance of sustainability, and this is one of the areas where we try to target what we do to serve society on a wider level. We've done a mapping of the goals where we are already working particularly closely, and we're trying to see how we can take that forward, and this is something that we're extremely proud of as well. Technology and innovation. I just said fundamental research is a driver of innovation, and this is very clear at CERN. We have three main instruments in particle physics. You will hear much more about them, and this is really where the technology development comes from. Particle accelerators, the Large Hadron Collider being our flagship accelerator, but also particle detectors, and you'll hear much more about this when you hear from CMS and from Alice, and of course large-scale computing. And from the technology in all of these three areas spring cutting-edge technologies that can be applied in society: magnets, material science, electronics, cryogenics, vacuum technology, AI, quantum, and all of this is is transferred to society at no cost. We already heard about the World Wide Web. So this was developed by Sir Tim Berners-Lee. You see him here. When he was working at CERN in the 1980s, he was part of the IT department. You see on the left-hand side, you see the first iteration of his proposal that became the World Wide Web. And it was so innovative at the time that he actually had to write 3 proposals before management of CERN at the time actually fully understood how innovative this was. And I was part of a seminar when the web turned 30, and some of the colleagues who had been working with Sir Tim at the time said that they didn't get it. It was so innovative at the time that it took several iterations before they fully understood. And then when it clicked, literally, now we all click, but it also clicked for management at the time, he was then given a little bit more time, and he was given a browser, a next browser, and he could build a World Wide Web. And we actually have that browser on display at CERN today. But in terms of impact on society, that goes much, much further. We already heard one of the areas where particle physics, applications from particle physics have had the greatest impact is in the area of medicine, where particle accelerators are used in treatment of cancer, protons, ions, and electrons. We also work on with machine learning to help, for example, develop software for autonomous driving. We have had a partnership with Volvo, which may not be immediately obvious. Why is CERN working with Volvo? And this is, of course, because we work on fast electronics and sensors that are also essential for improving autonomous driving. Detector technology is particularly important. We already heard about the PET scanner, which was developed in a collaboration between CERN and the University Hospital of Geneva in the 1970s. Now it's in all hospitals in the world. And some of the innovative pixel technologies now are used, for example, by startups to develop high-resolution 3D color X-ray imaging, which will then allow medics to see also the soft tissue when they do X-rays, which is extremely helpful for their clinical work. And interestingly enough, particle accelerators can also be used when it comes to cultural heritage to understand, for example, when you have old paintings, what are the different layers that have been put on a canvas over many decades or centuries. And there again, you can apply technologies that come out of particle physics. So this is really an incredibly vast range of technologies that have a very profound impact on society. We work underground, but some of the technologies also go into space. You see here what's called the TimePix detector, which is measuring radiation in the International Space Station. So you see that cutting-edge technologies from deep underground also go very far into space. Our biggest impact, though, is through the young people who come through CERN. It is an incredibly rich training ground for young scientists and also many, many other professions. At any one point in time, CERN has about 4,500 young people in different types of educational programs. We have an incredibly rich program for graduates. We have about 3,000 PhD students working with us. They're not employed by CERN, they're employed by universities and institutes across the world, and they come and they do their work at CERN. We have a very rich summer student program. We also have a program for high school teachers from across the world that come and develop further their skills and the types of experiments they can do with students in the classroom, which is an incredible multiplier because, of course, one teacher will touch hundreds and thousands of students. We run an extremely popular and successful competition, for example, for high school students that can propose an experiment. This is called Beamline for Schools. They propose an experiment that they can come and undertake at a beamline, and the winning teams come to CERN and to our partner lab, DAISY in Hamburg. And we have had over 20,000 students come through since this was developed, actually in the context of our 60th anniversary, so 10 years ago. Now, all of these young people come out with incredible skills and incredible knowledge and incredible networks, and they do not all stay in particle physics. And this is another plot that we're particularly proud of, because you can see when you look at the age distribution, the peak is at 27, and this is due to all the PhD students that are with CERN. You can also see then that it trails off. They don't all stay in particle physics, though you can see some of them do stay until they're in their 90s, so it's a very healthy discipline as well. But most of them actually go out into other areas of society, many into industry, other areas, research, also into finance, government, etc. And this is because the skills that they gain, not just technically, but also the ability to work together and to develop foresight, simulate, etc., is really prized in other parts of society. So the skills development is probably the most important impact and the most direct impact on society that CERN has. We also work actively to inspire the next generation. We know that the next generation is really interested in the big questions. We have a responsibility also to nurture their interest, not just selfishly for our own purposes in particle physics, but also because the world needs more skills in STEM. Jobs that require STEM are the fastest growing, and in many parts of the world we don't have enough young people who go into those professions. So it's very important that we try also to use the capacities that we have to engage them and to bring them on board. We have constructed a new education and outreach center that opened in 23. We've had just about 500,000 people come through now. We also have traveling exhibitions that go around to our member and associate member states. We've had some excellent exhibitions also in India, and we're of course very active on social media. So 70 years of incredible science, incredible technology development, and generating incredible engineers, physicists, etc. So what lies ahead? So the Large Hadron Collider, the first ideas about the Large Hadron Collider were presented in 1984, and it came really online in 2010, and we now have a physics program that runs until 2041. So we're talking 50, 60 years of lifespan of such big experiments. So we are already into looking at what the future holds. There is a process of strategizing so that the community can come together and determine what is the most promising, what are the most promising avenues from a physics point of view, and this is then eventually adopted by our member states in the Council. The last update took place in 2020, and there CERN was given the task, amongst others, to undertake a technical and financial feasibility study of what could be a future circular collider. And this is the one you see on the right. You see the Large Hadron Collider to the left, which is like a cute little toy accelerator compared to the next generation. This would be the most incredible instrument ever built by humankind, with incredible physics and technology development potential. The feasibility study is going to be finished now in 6 weeks, something like this, and will feed into the next strategy process, which is now ongoing. And what the community now has to figure out, and the task that they have, is actually to select the next big collider at CERN. And India, as an associate member, is part of that process, and it's an important voice to have in the process, and it of course speaks also to the incredible scientific tradition in India, that India is now part of shaping the future through the strategy process. India and CERN, an extremely fruitful, long-standing relationship dating back to the late 60s, early 70s, at the time pioneered by Tata in Mumbai, involved across the scientific program with the emphasis on CMS and ALICE. Also very important contributions to what's called the Worldwide LHC Computing Grid, which is the distributed networked computing infrastructure of CERN, which is spread across 40-something countries, 170 centers in the world, effectively a precursor of what is cloud computing. Today, this is the tool that was used to store, to distribute, to analyze the data. Very important contributions from India also to the construction of the Large Hadron Collider, also to research and development in accelerator technologies. And as a result of this, India was awarded observer status with CERN in 2002, and leading up to then India becoming an associate member in 2017. And this now means that India is a co-owner of CERN. CERN is part of the national research infrastructure. In India, it may be many kilometers away, but it is an integral part of the research infrastructure here and is used by Indian scientists exactly in that way. As I said, strong involvement across the experimental program with emphasis on ALICE and CMS, but also strong involvement in fixed target experiments, and also, and this is a very important point, a lot of work on research and development, and also a strong capacity when it comes to accelerator projects. And this is something that will also be particularly important going forward, given that there is now plans possibly for the development of a very large 90-kilometer ring that will also house an incredible accelerator. I just want to finish with a couple of points about how Indian talent is being integrated and using the educational and outreach opportunities that comes from CERN. This is very much a mutually beneficial relationship. We have been part of organizing teacher programs, student programs in India. We've had an Indian team win the Beamline for Schools competition in 2018. And when you think that there are teams from all over the world that compete, that's a very, very impressive achievement. We were part of the first Mega Science exhibition in 2019. This is an example of the traveling exhibitions that we host. We also host student groups at CERN. This is from last year, and you see here the beautiful Shiva statue that we heard from about earlier. We have a strong participation also in science outreach in India. You see here a lovely photo from Pune a little bit earlier this year, and we actually also, and this may not be very well known, but we actually also have Indian scientists that participate in art residencies at CERN. We have a program called Arts at CERN, where artists can compete and be embedded in CERN for a certain period of time in order to engage with the scientists and also develop incredible artworks. And we've had a couple from India also very recently. So the scientific journey continues after 70 years. CERN will continue to play a very crucial role in that. And importantly, India will be an integral part of this scientific and technological endeavor with us. Thank you very much.
So thank you, Charlotte, for these very fascinating talks and all this detailed information about the past, present, and future activities at CERN. We can address a few questions from the audience, if there are any. Yes, volunteers, can you please?
Yes, so I'm particularly, my name is Prasanna, and I'm MSc graduate in physics. So I'm particularly fascinated by how so much of money and resources were poured, especially after World War II, given that they would have spent a lot of their resources on other things. So how was the public and the government convinced that we should invest in this, or how did the scientists manage to take up this and convince the governments?
So specifically after the Second World War in general, sort of.
Specifically after Second World War, because the economies will not be doing great, and in general as well, both.
It's a very, very good question, I think, which speaks to how visionary both the scientists and the politicians at the time were, because you're absolutely right. You could say, well, is this really what we need to do now? And I think the answer to that is that's exactly what we need to do at a time like that, because fundamental research is really a driver of development, socio-economic progress. You need to have the fundamental research in order to also have applied research and in order to develop also on a socio-economic level. Obviously, some of this is also down to the persuasive powers of those who were involved at the time. But it is interesting that the scientists who brought this forward first were able to get the ear of the politicians at a very, very early stage. And I think it speaks not just to their persuasive powers, but also to the compelling nature of the project. And I think that still continues. You can have the same discussion today. There are many priorities, there are many things we need to invest in. But we will be doing ourselves and society a disservice if we don't invest in fundamental research, because the big jumps and the big transformations and the big innovations, they come from fundamental research. And I think there was an understanding that needed to be part of the equation if you wanted to rebuild. So I think it was an understanding of the value and the potential impact of science that really was the argument at the time. And I'm convinced it still is today.
Thank you.
Check. Two quick questions. Can you list down the top 3 biggest unanswered questions that CERN will try to answer going forward in the next probably the decade or so? And I noticed that most of your members are in the neighborhood of Europe. So I'm just wondering, what does it take to become a member, and what does it take to become an associate member? Thank you.
Both of those questions are excellent. And the first one, I will hand over to my esteemed colleagues from Alice and CMS. I'm looking at them so they know that this is coming. But there are incredible, outstanding questions in terms of the asymmetry between matter and antimatter, dark energy. The reality is that we only understand 5% of what's out there in the universe. 95% is a question mark. We call it dark energy, dark matter. Dark because of our ignorance, dark because it doesn't interact with the instruments that we have. We don't understand gravity. Gravity is the force that is most obvious to most of us, but it's the force that we understand the least. So there are really, really big questions. I think one of the great truths in life is that the more you know, the more you realize you know very little. And I suspect that probably in the 1950s we thought we understood about 95% and we only had 5% to learn. Now the proportion is the other way around. But I know that my colleagues will come back to the sciences more in detail. So the question about the geographical distribution is a very good one. So CERN was initially, it's in the name, European. But since 2010, there's an active enlargement policy also to bring it beyond the European borders. This is also what the associate membership instrument is for those who may not necessarily wish to invest exactly at the same level as a full member state. The associate membership allows countries that may be further away, that may have different priorities, to still be part of the family. They contribute at a lower level than the members at the full level. Then they have rights and obligations in proportion to what they contribute. But membership is actually also open outside of Europe. Israel is the first non-European member state to join. And we see a lot of growth and a lot of interest. Of course, India, not surprisingly, was a first mover, one of the first associate member states. But recently we brought on board Brazil as the first associate member state in the Americas. Chile is in the process also to become an associate member, so we see a lot of growth also now in the Latin American region. And this is where the associate membership status is a particularly valuable framework for countries that wish to be part of CERN but may not wish to be full members can really engage. But it, as you saw, it's an open collaboration, 110 nationalities, and we see interest across all continents.
Thank you.
You showed a graph where you said that the member is doubled. So in the same graph, around 2070, there was a dip. So can you explain that?
Ah, yes. So this has to do with the operational nature of the lab. So there are times where we have longer periods, long shutdowns, where the machine is stopped for 2, 3, 4 years for maintenance, upgrades, etc. And during that time, there's sometimes a smaller number of scientists that are coming to CERN. They may be working with CERN, but from their home institutes. So when there are long shutdowns, we often see a small dip. Of course, there was a dip also in the pandemic that has come back. But you see some of the dips around the long shutdowns.
Okay.
Yeah.
Good evening. So, given the political scenario that is happening right now in Europe, and with Israel moving things, Germany, and then Donald Trump is at the helm of American government, now I believe there are more concerns over financial economic crisis and scientific development may be hindered. How confident are you and CERN that the international collaboration will still maintain and progress will still be our long-term goal?
It's a very, very good question. And of course, we live in a very fast-moving world. Tectonic plates are moving in geopolitics at the moment. I think we need to look at the example of history. So member states and also our associate member states have really been with CERN through ups and downs, through Germany, reunification, big impact. The financial crisis have come and gone through a Cold War, then the challenges in the late 2008-9 financial crisis, etc. I think what we have seen is that member states are really committed to the project. They also understand that this is a long-term thing, and the investment pays off over the long term. There is an understanding of CERN both as an incredible scientific adventure, as an incredible technological adventure, but also of the symbol of what CERN is as a place where people from across the world can come together and do incredible things, where we can show what we can do when we don't focus so much on what divides us, but on what actually unites us. As a recent example, obviously CERN was impacted also by the fallout of the Russian invasion of Ukraine and high inflation that followed. And in that context, even if member states were having legitimate challenges financially at home, they actually voted for a special contribution to top up the CERN budget so that the impact on the organization would be felt less, which I think testifies to an incredible support for the organization, even in very, very difficult circumstances. So I think we look to history and we're confident by looking at what we have gone through, and we think we can do the same for the future.
So, yeah, thanks again. Thanks, Sarla. Okay, so I am glad to invite our next speaker, Professor Bedango Das Mohanty. Professor Mohanty is a senior professor of physics at the School of Physical Sciences at Nizar in Bhubaneswar. He currently holds the position of deputy spokesperson of the ALICE experiment at CERN and has previously served as the deputy spokesperson of STAR experiment at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, USA. His research focuses on the phase diagram of quantum chromodynamics and the properties of quark-gluon plasma. His prolific contributions to science are reflected in his more than 900 publications in international journals, alongside mentoring 20 PhD students, 16 postdoctoral students, and 23 master students. His remarkable academic journey has earned him numerous prestigious awards and honors, including being elected as a Fellow of the American Physical Society in 2020 and as a Fellow of all 3 Indian Science Academies in 2017. Professor Mohanty has also received India's top science awards, including the Infosys Prize in Physical Sciences in 2021, the Bhatnagar Prize in 2015, and the Swarna Jayanti Fellowship 2010. His recognition as a J.C. Bose National Fellow by the Department of Science and Technology speaks volumes about his extraordinary contribution to the field. Today we are fortunate to hear from Professor Mohanty, and please join me in welcoming him.
Thank you. Hello, can you hear me? Yeah. So thank you very much for this kind introduction, and thank you to the organizers for giving this opportunity to present before you some exciting results from one experiment in one facility at CERN called LHC. So the title of my talk, by the way, the talk is mostly oriented towards the younger audience. So I will be trying to explain concepts using analogies. The title of this presentation is Recreating Microsecond-Old Universe Conditions in a Large Ion Collider Experiment, that's ALICE, a perfect fluid of quark and gluons. So let me first start by giving you some scales in our universe. Earth is perhaps the only habitable planet that we know in our universe, and it's already quite big. Its diameter is 12,742 kilometers. It's a third planet in our solar system, and if you look at the span of our solar system, it's about 150 million kilometers. The sun and our solar system is part of a galaxy called as the Milky Way. It actually has millions of such stars, forms a galaxy, and millions of such galaxy form the visible universe, and the observable universe has a diameter which is a staggering 10 to the power 26 meters. Now, what we deal with is what are the basic. The universe is very big, but what are the basic building blocks of this universe? Now, all of you have already studied in school that it was proposed that is the atom. It was proposed by Dalton, that is the atoms. The word atom means something which cannot be further subdivided, is the basic unit that make up the visible matter. But later on, due to work of Thomson, who discovered the electrons, Rutherford and his set of students who figured out that atom has a positively charged nucleus, and inside the positively charged nucleus are protons, and Chadwick found that there are neutrons. So at that point of time, the basic building block, the fundamental units which make up anything that you see around, were electrons, protons, and neutrons. Then scientists did a scattering experiment similar to that of Rutherford and figured out that protons are actually made up of still smaller particles, the quarks and the gluons. So as of now, what we know is most of the things that you see around are made up of particles like electrons, quarks, and gluons. However, no free quark and gluons are seen in nature. The quark and gluons are always confined, imprisoned inside particles like protons, neutrons, pions, kaons, or what we call as hadrons. The question is, if that is the case, how do we study its properties? And why do I say this? I'll give you an analogy. Let's take the example of water, which every one of you are familiar with. It's made up of hydrogen and oxygen. Hydrogen is a fuel, it burns. Oxygen supports burning. Water extinguishes fire. So if I give you water and ask you to tell me what are the properties of hydrogen, oxygen, properties like viscosity, conductivity, it's very difficult, right? So best way is to have a free system of these components and you can study its properties. Same is true for us. All of us are made up of quark and gluons and we want to study properties of something which we are made up of. So we need to create a free system, deconfined system of quark and gluons. Now, we don't have that in nature. But the question is, were these quark and gluons ever free? Well, that brings me to this Big Bang model, which describes how the universe evolved. The universe has evolved over 13.8 billion years. Now you may ask, why should I believe that this model describes the time evolution of the universe? Well, this model makes some predictions which has been experimentally verified, and 3 of which I have shown here. That the universe is expanding, that's what has been observed. The relative abundance of light nuclei are pretty well predicted by this model. This model also tells that there should be a cosmic microwave background radiation, and that has been discovered. So that's why we believe that this Big Bang model is a good model which tells us about the time evolution of our universe. If you look at this box, it has small t, the time, temperature, and energy. And I draw your attention to a microsecond old universe. You can see that the quark and gluons, the basic building blocks of matter, were free, and the temperatures were 10 to the power 12 Kelvin. So let's contrast the situation in a microsecond old universe and the current time. So in a microsecond old universe, the temperatures were of the order of 10 to the power 12 Kelvin. The quark and gluons were free. They formed a plasma of quark and gluons. Current universe, 13.8 billion years old, temperatures about 2.7 Kelvin. The quarks are confined. No free quark is seen in nature. So the next question is, can we recreate these microsecond old conditions in terms of temperatures in the laboratory? So scientists figured out that yes, it is possible. It's possible by colliding heavy ions at very high energies. And you could reach temperatures of the order of 10 to the power 12 Kelvin. Matter melts into its basic building blocks, free state of quark and gluons, and you can then study the properties of particles which each one of us are made up of. And the best such facility is the Large Hadron Collider, the largest particle accelerator in the world. You heard it's 27 kilometers. Now, just to tell you how fast things move so that they collide and produce this, a proton roughly moves this 27 kilometer 11,000 times 1 second. That's the speed with which you move these particles and make them collide. And why do we do it? We want to create a free system of quark and gluons, mimicking a microsecond old universe, and then study its properties. Now, since we are celebrating CERN 70, I must say that India has significantly contributed to the very building of LHC in all its aspects, in accelerator, in computing, in detector, in electronics. all its aspects. And these photos show some of the contributions which India has made. If you want a quantitative number, that's again just a snapshot of the quantitative contributions which India has made to LHC. So we are part of LHC and very much is a big contributor to the LHC program. And you already heard all this has been possible because of the attempt or because of the active involvement of Department of Atomic Energy, which first went into an MOU, and then India is now an associate member at CERN. So that was just to tell you that we have contributed from the very beginning of the LHC activities. Now coming to one experiment which is in this Large Hadron Collider facility. The other, one of the other experiments you will hear in the next talk is the ALICE collaboration. It's a collaboration of 39 countries, 163 institutes, and close to 1900 members. And here also, India is one of the founding members of this experiment. From the very concept proposal stage, Indian institutes has been involved in setting up this experiment. And currently, these are the institutes which are participating from all over India as part of this experiment and contributing to all its aspects. So now let me come back to the Big Bang model, and now I call what we do in the laboratory as little bangs. Okay? We are trying to mimic the conditions of early universe by colliding heavy ions at relativistic speed. So how does the system evolve? So two heavy ions like lead ions are accelerated at relativistic speed. So often they are shown as Lorentz contracted along the direction of motion. They come and collide, and a large amount of energy is deposited in a small volume. So the energy density is large, and you must have come across Stefan-Boltzmann law, which tells energy density is proportional to T to the power 4. So you expect the temperatures to be high. If the temperature is of the order of 10 to the power 12 Kelvin, matter melts into its basic degrees of freedom, the quarks and gluons. This system starts to expand. As it expands, it does some work. So the temperatures will fall. And when the temperature falls below a certain value, where quark and gluons can no longer be free, current universe, they are not free. So then these quark and gluons have to be imprisoned or confined inside particles called hadrons. And that phase is called as hadronization. These hadrons continue to interact, and a time will reach when no longer they interact among themselves. They free stream, come and hit the detector. Using the information of what we detect, we have to retrace back all this process and try to see whether we formed a free system of quark and gluons, whether the temperatures were 10 to the power 12 Kelvin, and then study its property. Why it's very challenging is the system that is formed is femtometer in size, 10 to the power minus 15 meters. And the duration for which it stays is Jeptoscale, 10 to the power minus 21 seconds. So that makes it extremely challenging to do this experiment and to draw science conclusions. Anyway, we have done that, and ironically, to detect this femtometer scale experiments, okay, let me just see. You have to build meter scale detectors, 10 to the power minus 15 meter scale systems, but you need few meter scales detectors. This is the ALICE detector at LHC, and you can just see how huge is it compared to a person making some measurements, how complex. It's a state-of-the-art detector which tries to do the physics that I explained. So it's huge in terms of the size. It's 26 meter long, 16 meter high, 16 meter wide. It's about 50 meters underground, weighs 10,000 tons, and of course costs quite a bit also. It's about 100 million Swiss franc. It is with this experiment we try to do our physics. One of the most interesting aspect of our experiment is we are able to detect particles, identify the particles which come out of this collision and hit our detector. And that we do by two techniques. When a charged particle passes through a medium, it loses energy, primarily through Coulombic interaction. And the detectors, if it can measure the energy loss, and we can plot it as a function of momentum of the particle, then the different particles will show different bands. That the energy loss of charged particle goes inversely as the square of the velocity. And for a relativistic particle, for a fixed momentum, it depends on the mass of the particle. And that's how you can figure out the different particles. This plot actually made it into the particle data group. You can also use the time of flight technique. Time taken by a particle to traverse a fixed distance can be used, again for a relativistic particle. Time is distance by velocity, and you can see for a given momentum, it depends on the mass of the particle. So time of flight as a function of momentum allows us to identify particles. Dominantly, 5 kinds of charged particles reach our detector system, and 2 kinds of neutral particles. However, there are many particles which decay into these stable particles or charged particles which ultimately fall on our detector. And then what you do is make use of Einstein's energy mass relation. E square plus, what is the Einstein's energy mass relation? E square is equal to m square plus p square, right? So you can use invariant mass technique to reconstruct the parent particles. And these are all the kind of different particles we detect over a wide range of momentum to do our science. So first thing that I want to convince you is that we have measured temperatures which are 10 to the power 12 Kelvin. Now we can't use a sensor to measure such high temperature because matter melts into its fundamental units. So how do we access temperature of our system? So we make use of the fact which you have read in thermodynamics that for a thermal system, if you plot the population of the particle as a function of its energy or momentum, it's a Maxwell-Boltzmann distribution. It's an exponential distribution, and the slope gives you the temperature. That's how we extract the temperature reached in our system. But we produce so many kinds of particles. Which one should we choose so that it reflects the temperature of initially formed quark and gluons? So a particle we choose, one which does not interact with the system. It faithfully carries the information and reaches our detector. One such particle is photon. It doesn't undergo strong interactions. But then we are land with another challenge. There are many sources of photons. We are interested in photons which are coming from quark and gluon interactions. So scientists have to very painstakingly subtract all these contributions and finally filter out, this is the counts as a function of momentum of photons which generally come from interactions of quark and gluons. It's an exponential distribution, the slope of which turns out to be more than 300 mega electron volt. 1 mega electron volt is 10 to the power 10 Kelvin. So we have reached temperatures of 10 to the power 12 Kelvin. We have reached conditions which were similar in terms of temperature as the microsecond old universe. And subsequently we figured out that indeed we have formed a matter which has a free system of quark and gluons. Just to give you a perspective of the temperatures that we reached in the laboratory, the lowest recorded temperatures are of the order of 10 to the power minus 10 to minus 6 Kelvin. The temperature of this universe extracted from the cosmic microwave background radiation, it's a perfect Planck blackbody radiation. You could fit it and extract the temperature. It turns out to be 2.7 Kelvin. The temperature of this room is 300 Kelvin. The temperature of the surface of the sun is 6,000 Kelvin. The core of the sun is 1,000,000 Kelvin. The temperature from a thermonuclear explosion can take you to 10 to the power 9 Kelvin. And what we achieve at the Large Hadron Collider by colliding two nuclei is a staggering 10 to the power 12 Kelvin. If you still do not believe, and just for fun's sake, it has entered into the Guinness Book as the world's highest artificial temperatures recorded in the laboratory. So what we have managed to do is reach conditions which mimic the early universe in terms of 10 to the power 12 temperatures, where matter melted into its fundamental constituents, the quark and gluons. Now we can study its properties. And the one property I am going to discuss today is the viscosity. What is the viscosity of the system of quark and gluons which we have formed at these experiments? For that, let's see what is viscosity. Viscosity is nothing but resistance to flow. If you look at water or honey, honey is more viscous than water because water flows more smoothly than honey. Now, if you look at this experiment, which I'm told has been happening since 1927, here is a funnel. It has pitch, the quantity which is used to make roads. There is a beaker and it is shielded from the outside environment. And so far, only 8 drops have fallen from this funnel to the beaker, right? Since more than 80 years. And nobody has ever seen exactly when the drop fell into the beaker. It stays for years like this and then suddenly it falls. Of course, now we have CCTV cameras, we can record it. So it's a highly viscous fluid. It's about 230 billion times more viscous than water. Now, is there any other extreme? Can there be some lower bounds to the viscosity? First, to compare viscosity across different fluids, we use kinematic viscosity. Viscosity divided by the density of the fluid, or a quantity proportional to the density of the fluid. So, the quantity that I will be discussing is coefficient of viscosity divided by entropy density, because entropy density goes as number density. Okay, that's what I call as kinematic viscosity. Now, if you take the expression given for coefficient of viscosity by Maxwell, number density, momentum and mean free path, and make use of uncertainty principle in quantum mechanics, you can quickly see that there is a lower bound of kinematic viscosity a fluid can reach. More sophisticated string theoretical calculations suggest that this bound is of the order of 1 over 4 pi. The question is, what is the kinematic viscosity of quark and gluons, the basic unit which each one of us are made up of at that high temperature? First thing we have to do is to devise an observable which will measure flow, because viscosity is resistance to flow. So you have to take my words that after a lot of efforts, that observable has been fixed, that's flow, as a function of momentum. These are the experimental data points. Now we want to extract the kinematic viscosity. So we will compare it to theory calculations, basically solving energy momentum conservation equation with kinematic viscosity as a parameter. So these curves show the theory calculation. For example, this one is for kinematic viscosity 0. Now what I will do, I will gradually dial up the kinematic viscosity. So the flow should reduce, right? And that is what we see as you dial up the kinematic viscosity to 1 by 4 pi. These are the lower bounds. 2 by 4 pi, 3 by 4 pi, the flow reduces. Now look where the data is. It's closest to the lower bound expected from natural principles. If you compare it, the kinematic viscosity as a function of temperature for the known fluids in nature, this is where it lies for a system of quark and gluons. These has been extracted using the ALICE data and comparing it with theory. It is the smallest kinematic viscosity recorded for any fluid. And that's why we say we have created a system of perfect fluid. So not only we have created conditions which mimic early universe in terms of temperatures, where we have a free system of quark and gluons, we have gone ahead and measured its properties. One of the property is the kinematic viscosity, and it turns out to be a perfect fluid. Now let me switch quickly to the societal aspects a little bit. This you already saw. I didn't know that the similar formulation will come. Our experiments just in the previous talk, our experiment stands on 3 foundations: the computing, detectors and accelerators. Each of them state of the art in technology. Each of them have been put together by brightest of mind, of course it will have societal applications. I'll give one example from each of them, then we will play a video. Basically what I and the previous speaker said, it is there in a CERN video. I hope you all will enjoy. So we'll start with one example which you already know. Actually all the three you have heard in the previous talk. So one is the World Wide Web. Basically our experiment leads to a huge amount of data. We need to share and exchange information. And that was one of the perhaps the motivation for the World Wide Web to be born at CERN. Soon CERN realized its potential and released it to the public domain. And I hope you would agree that very few other technological advances in history have more profoundly affected the global economy or the way we interact than the World Wide Web. On detectors, we build detectors which detect minutest of the particles traveling with fastest of the speeds. We need excellent spatial resolution and timing resolution, and that makes it very important for medical imaging purposes. Soon you will see the two-dimensional black and white X-rays being replaced by a three-dimensional image of human body, tissues and cells with color contrast, and that would help in medical imaging immensely. And the accelerators, which is able to collide protons over a distance of traveling 27 kilometers, we can precisely reach the diseased tissues, cancerous tissues, for example, and impart energies, and radiation therapy can be used for cancer treatment. In doing so, using a principle of what is called as the Bragg curve, you will hear in the video, we will least affect the good cells and tissues on the path. And that is what makes radiation therapy an attractive method for treatment of cancer. So I'll now show you a video. I think it will be played somewhere. Okay. And then it has its own audio, so relax and enjoy, and then after that I will take just 2 minutes.
The Large Hadron Collider, the largest and most complex tool of modern physics, 27 kilometers circumference, 100 meters below ground, accelerating and colliding beams of particles whizzing around at nearly the speed of light. What for? To study the structure of the universe and its underlying principles. To accomplish this feat, scientists invented new technologies that were unimaginable just decades ago. This process has led to innovations in many fields, and sometimes disruptive revolutions that have changed our lives. Medicine is a prime example. Ever since William Conrad Röntgen's accidental discovery of X-ray in 1895 and their immediate application to look inside the human body and then treat cancer, physics research has fueled medical innovations. A year later, Henry Becquerel discovered natural radioactivity in uranium, a spontaneous decay process through which some elements emit energy, or radiation, in the form of particles. Soon after, Pierre Curie and Maria Skłodowska-Curie discovered two new and highly radioactive elements, radium and polonium. Applications of radium salts were very quickly used to treat surface or body cavity tumors. Even some of the most fundamental physics discoveries have found their way into the hospital. Antimatter, a mirror twin of ordinary matter, is not just the subject of science fiction movies. It's also not something that is only found in physics laboratories. The anti-electrons, or positrons, that were postulated by Paul Dirac in 1928 and discovered by Carl Anderson in 1932 are actually used in a special type of medical imaging. Positron emission tomography, or PET, allows doctors to identify anomalies in the metabolic activity of the body, and hence to diagnose various diseases.
L'idea di utilizzare queste particelle accelerate o da ciclotroni o da sincrotroni per la terapia del cancro è dovuta a un grande fisico, Bob Wilson.
In 1946, Robert Wilson, first director of Fermilab, proposed to use protons for cancer radiotherapy. Protons can target tumors more precisely than X-rays since they release most of their radioactive dose in the so-called Bragg peak. Today, particle accelerators, particle detectors, computing and data analysis methods are ubiquitous in hospitals and medical research centers. Conventional radiotherapy with X-rays is widely available at low cost. A limited number of facilities worldwide offer radiotherapy with protons, and an even smaller number with carbon ions, allowing to treat some of the most challenging types of tumors. New technological options are being explored to make particle therapy more widespread and affordable. New treatment modalities will also become possible, such as flash radiotherapy. Particle accelerator technology also supports nuclear medicine, which uses radioactive substances called radioisotopes for treatment and diagnosis of many diseases. A large fraction of these radioisotopes is still produced by research reactors built in the 50s and the 60s, and particle accelerators are becoming a viable option to ensure a steady supply of medical radioisotopes. Accelerator-based installations can produce innovative medical radioisotopes, which can provide more personalized diagnosis and treatment options.
The first time a PET image was ever taken at CERN of a small animal was in 1977.
Today, PET scanners use detectors based on scintillating crystals, similar to the ones used in particle physics experiments. And thanks to technologies developed initially for the LHC experiments, X-ray imaging has moved from black and white to color, providing more information. Computing and simulation techniques developed for particle physics have already been adopted in medicine. For example, to develop radiotherapy treatment plans or to simulate complex biological systems. Artificial intelligence provides new opportunities, from spotting anomalies in brain imaging to optimizing cancer screening or stroke management to preserving patient data privacy. For more than a century, research in nuclear and particle physics has acted as a trailblazer for disruptive technologies, which in turn have enabled crucial innovations in medicine. This collaboration is far from over.
Okay, thank you. So let me see what happened. Okay, let the slides come. I have 2 more slides. So what I wanted to say is, in our quest to know more about nature, that's what we do in our experiment, leads to building things that are at the forefront of cutting-edge technology. It is this technology which has widespread applications in society. So on the occasion of CERN 70, CERN is an international laboratory, and it is a place where we probe the fundamental science. We make use of the world's largest and most complex scientific instruments to do these experiments. One such facility is the Large Hadron Collider, and in that one such experiment is ALICE. What I have today discussed with you is that in ALICE we have managed to recreate the temperature conditions of a microsecond-old universe. We have formed a free system of quark and gluons which allowed us to study its properties. One such property which I discussed with you is the kinematic viscosity, which is the smallest among any known fluids. We are now making measurements of its conductivity, diffusion coefficients, and so on. If young people, you are interested about career opportunities at CERN, do look up at this web page. I'll end by going back to that Big Bang model page because there are so many young people in this audience, and this is how our universe evolved to current stage. And our funding agency, the Department of Atomic Energy and Department of Science and Technology, has supported scientific programs where you can actually try to study in time slices of this evolution. We are here studying microsecond and smaller time scale of the evolution of the universe. If you want to know more about how the first nuclei got formed, a few minutes old universe, you can join the efforts in Facility for Antiproton Ion Research at GSI Darmstadt. If you want to know how the formation of first stars took place, 100 million years old universe, you can join the square kilometer array based experiments. If you want to know about how the structure of the universe came about, a 500 million years old universe, you can join 30-meter telescope efforts. If you want to know how fusion process operates, the main source of energy, about a billion years old universe, you can join ITER experiments. If you want to know more about gravitational waves, black holes and neutron star mergers, you can join LIGO. Tremendous opportunity for young people in mega science. Of course, I would like you all to join the CERN activities. Thank you very much for your attention. Thank you.
Thank you very much, Professor Mohanty, for these very interesting talks and giving an overview of all the opportunities one can get. We can address a couple of questions from the audience. Yes, volunteers.
Hello, sir. If Alice can recreate the early universe, can we able to analyze why matter dominated antimatter in the universe and about the extents of Big Bang? Dark matter and dark energy.
Yeah, these are very fundamental open problems. And Alice addresses it in some way. CMS addresses it in a more direct, in a different way. And there are also direct experiments to detect dark matter. So these are still unresolved questions, but important questions in science. Antimatter, matter asymmetry, and dark matter, these are all fundamental questions.
Thank you, sir.
Good evening, sir. It was a nice presentation. And my name is Sanjay Balaji from SRM Institute of Science and Technology. I have one particular doubt is how the quark and glucons connection, it produces large amount of temperature. How can it contribute? The large amount of, whether it is converted into any other form of energy or such that?
No, so it's by pumping in by colliding the two nucleus, you pump in a large amount of energy. And this energy leads to this particle production. So that's the concept basically. I mean, so, yeah.
But my doubt was, it produces large amount of temperature. How can the large amount of temperature is not getting wasted? Like, we should not get wasted the temperature, right?
I see.
The heat energy.
But it stays for Jepto scale, 10 to the power minus 22, 23 seconds. So very difficult to tap that kind of, yeah.
We can have one last question.
Hello, sir.
Sorry to interrupt. You have asked to this previous speaker, maybe another.
Ask it nicer.
Yeah.
I wanted to ask how experiment in LHC or something can be used to unify quantum mechanics with gravity. Means this is the last puzzle. That means what are you looking for?
That I don't know the answer to that. Sorry about it. Maybe others can chip in. That's a difficult question to answer.
Yeah,
I don't know the answer.
So FCC is the new
that's the next generation.
Is it what it is targeted for? Means to
maybe indirectly.
See gravitons.
One of the possibilities could be that.
Okay.
Okay, thank you for all the questions, and let's thank Professor Mohanty again. I'm delighted to introduce our final speaker of the event, Professor Gauthier Hamel de Montchenal. Professor Gauthier is a renowned physicist at CEA Paris-Saclay in France. He is currently the spokesperson of CMS at CERN. His impressive career in particle physics began with his PhD as part of the Delphi experiment at LEP, where he focused on the search for the Higgs boson. He is a founding member of the Babar International Collaboration at the Stanford Linear Accelerator Center, SLAC, California. He participated as the scientific coordinator of the experiment in 2001 to revealing the phenomena of matter-antimatter asymmetry, a CP violation, in beauty quark disintegration. It was the experimental verifications of the theoretical prediction by Kobayashi and Masukawa, and that won the 2008 Nobel Prize in Physics. Professor Gauthier has been an active member of several key committees in the field, including the SPS committee at CERN, and currently serves on the High Energy Physics Board of the European Physical Society. He has made significant contributions to the online software for the ECAL laser monitoring system, co-convened the electroweak physics analysis group, chaired the publications committee, and now currently a spokesperson of CMS. Professor Gauthier's deep expertise and leadership in particle physics make him an invaluable figure in advancing global scientific collaborations and discoveries, and we are very fortunate to hear from him today. Please join me in welcoming.
Okay, so good afternoon. It's a great pleasure to be here today. I don't think it works, yes. So I'm going to talk about what has been called earlier today the God particle. It was named as the God particle by a Nobel Prize, who was the director of Fermilab, a great laboratory in the US, Leon Lederman. But in fact, when he called it the God particle, he said the goddamn particle. And then it was shortened into God particle, but I think it has nothing to do with God. So, but the Higgs boson has to do with the origin of mass. And that's something that you have heard about, and I will try to explain in certain, and in the frame of the CMS experiment at the LHC. So thanks to Beganda, a lot of the introduction has already been done. So in particle physics, we have this very nice model, which is called the standard model of particle physics. And this is a theory which describes the elementary particle. When we talk about elementary particles, and Beganda talk about that, we are really talking about, I don't know if the pointer works, we are really going about the ultimate particles, the quarks, which are constituting the protons and the neutrons that we call the nucleons, and the electron. As far as we can tell, the electrons and the quarks do not have a substructure. So this is something that we are trying to find out, but at the moment we consider that those particles are elementary. And you can see here, so I don't know if you are familiar with logarithmic scales, but you can see here that if you want to go into the art of matter, to go into studying the nucleon, for instance, you need to go at higher energy. So that's why we say that the particle physics is also the high energy physics, because if you want to study very small objects like the quarks and gluons and all the particles in the proton, you need to go at energy which are giga electron volts or higher. Okay. So these are the particles of the standard model, all elementary particles. We have talked about the quarks and gluons already. And now we'll talk also about the leptons. The electron is the lightest lepton, but there are also the muon and the tau. And as you can see, there are three families of quark and gluons. So the quark and gluons, as what we call the fermions, which are the particles of matter, and they interact by exchanging what we call bosons. So bosons come from the great physicist, Indian physicist Bose. So they are called bosons, and there are 4 types of bosons. You know the photon, of course, the gluon that we've talked about, and 2 bosons which are very heavy, the W and Z bosons, which are transmitting the weak force. And there is another boson here, which is a different type of boson, because this one is a scalar boson instead of a vector boson, the Higgs boson. So if you look at this mug here, you will see a formula which seems to be complicated, but in fact it is quite simple. And this formula contains most of the standard model. In fact, it contains the part which describes the interactions of the W and Z boson and of the photon that we call the electroweak theory. So you just need 4 lines to describe all of the interactions with the electroweak theory in the standard model. And all these lines you can explain, but the last line here is describing the dynamics of the Higgs boson, what we call the Higgs field. And in this dynamics, you have a function here of the field phi, and field phi is the Higgs field, and this function here is called the Higgs field potential. And that's the key. This Higgs field potential is what makes the whole mechanism at the origin of mass work. Why? Because this Higgs field potential has this kind of form, right? It has this kind of shape. It is symmetric around the symmetry axis, which is the vertical axis, but the minimum is not on the symmetry axis. The minimum is separated from the vertical axis, and that we call the spontaneous symmetry breaking of the electroweak theory. So on the next slide, I will try to explain what is this breaking of the electroweak symmetry. So you can see here what happens before the symmetry is broken, and here what happens after the symmetry is broken. And the transition between those two situations is what we call a phase transition. This phase transition is the electroweak phase transition, and it happened at the temperature which was at the 10 to the 15. So to compare with what you said just before, it is just a little bit hotter than the 10 to the 12 that we were discussing in the previous talk. So 10 to the 15 is the temperature of this transition, and in this transition you see that the Higgs field potential, which was symmetric with respect to the axis, but with the minimum, which is also on the axis, became stayed symmetric with respect to the axis, but with a minimum which is displaced with respect to the axis. And this is the electroweak symmetry breaking of the electroweak symmetry. So what happens after the electroweak transition? The W and Z bosons, which are the transmitter of the weak force, becomes extremely heavy, and the weak force stays confined inside a very small distance, which is the distance typically of 1/1000th of the size of the nucleon. It's a very heavy particles, but the photons stays massless, which means that electromagnetism stays with an infinite range. And that's exactly why the electromagnetic force and the weak force are completely decoupled after the electroweak transition. So this is the point in time in the history of the universe was when one interaction, electroweak interaction, separates into the electromagnetism and the weak force. What happens also is that all the particles of matter that I described just before, the leptons and the quarks, also acquire mass. And how does it work? It's quite simple. A particle with no mass goes at the speed of light in vacuum. So if a particle interacts with this, what we call here the Higgs condensate, then it will lose a little bit of time. It will be slowed down in the propagation in vacuum, and therefore V is smaller than C, and the particle has a mass. So in some sense, the interaction of particles moving into the vacuum and interacting with the non-zero Higgs condensate here creates mass, creates inertia. And that's where mass appears in this mechanism. So there is another prediction of all this theory is the existence of a scalar boson. It must exist, a scalar boson, which couplings, interactions with the other particles are completely defined. It must be coupled to fermions proportional to the mass and to bosons proportional to the mass squared. So this prediction is very strong. The only thing that was not predicted by the theory is the mass of this particle. So this is what you show, except that in my representation, time flows from right to left, and energy flows from left to right. So the Big Bang is there, and today we are here, and you can see the temperature which goes from a very large number to 3 Kelvin here. We are talking here of this line here, which corresponds to 10 to the 15 Kelvin, and this corresponds to 1% of a nanosecond, which is 10 to the minus 11 second. So it's a little bit just before the time of the quark and gluon plasma era. And this is the time, if you look here at the 4 interactions, this is the time where the weak nuclear force and electromagnetism get separated. Right? What happened before, we don't know. That's what we call this beyond the standard model. But we think that at some point, the 3 forces are going to unify in what we call the ground unification. And if this happens, it has to happen somewhere for an energy of 10 to the 15 GeV, which corresponds to this 10 to the minus 35 second. Okay. And then there is a wall where gravitation breaks. We know that general relativity is not valid beyond this wall. This is what we call the Planck wall, and this is 10 to the 39 GeV. Okay? So now let's come back to the mass of the particles, and here you have the same scale of energy from very small energy, micro electron volt, kilo electron volt, MeV, GeV, which is the mass of the proton, some TeV, which is the energy of the LHC, and here the Max Planck, the Planck energy 10 to the 19 GeV, and the ground unification scale 10 to the 15 GeV. And here you can see all the 12 particles that I showed you before and the different vector bosons. And you can see that they are all in the same region between some hundreds of MeV and some hundreds of GeV, right? So it's quite interesting to see that all the particles are very grouped in this plot, except for the neutrinos, which are called the ghost particles as well, and perhaps have something to do with the Higgs mechanism, but it's not completely sure, and we are trying to find out. Okay. What's interesting also is that you have these 4 particles, very massive particles, the W and Z boson, the Higgs boson, and the top quark, which seems to have approximately the same mass, around 100 GeV. So these particles have been discovered in the last 30 years. So these 4 particles, the W boson, the Z, the top quark, and the Higgs boson. It started with the discovery of the W and Z boson in 1983, and it led to the awarding the Nobel Prize to the discoverers Carlo Rubbia and Simon van der Meer at the time. Then in the 90s, CERN operated this very nice accelerator, E plus E minus collider, called the LEP, where the Z boson in particular was studied in very much details. And here you can see, for instance, that it was determined that the number of neutrino families was exactly 3, a very important result. There are 3 families of neutrinos. Thanks to all the measurements done at LEP, it was possible to predict the mass of the top quark, which was done. So it's the blue line here. These are the prediction of the top quark mass. And here you have the measurements of the top quark, which were done at the Tevatron by the CDF and D0 experiment at Fermilab in the US. So you see the W boson, the Z boson, the top quark, and with all this data, it was possible to predict with some uncertainty the mass of the Higgs boson. And after the first years of running of the LHC, we are even able to restrict the possibility for the Higgs boson into this very narrow band here between 120 and 130 GeV. That was the only place where, if it exists, the Higgs boson should have to be found. And indeed, it was found at 125, just in the middle of this band. So this was announced in 2012, on the 4th of July, and you can see here the 2 spokespersons at the time of the 2 experiments, Atlas and CMS. Fabiola, you have seen already. She's now the Director General of CERN. And Joe Incandela is a professor at Santa Barbara in the US. And they presented this very nice result. The first signal of the Higgs boson into when it decays to 2 photons here in Atlas. And here the example of a signal in CMS, where the Higgs boson decays into 4 leptons via a 2Z boson. So this was a discovery of a scalar boson at 125. It took a little bit of time to make sure that it was actually the Higgs boson, but now it is confirmed. And this Higgs boson is really important because it proves the existence of the Higgs field, which is responsible for the mass of all the particles. So all happened at the Large Hadron Collider, so we've seen that before, and we know that there are 4 experiments on the Large Hadron Collider, and the 2 general purpose experiments that discovered the Higgs boson are Atlas here, close to Mérin, and on the other side of the ring, close to JEX, the CMS experiment, which I'm going to talk about now. So here it's the same view, but as seen from CMS, so as seen from the Jura mountains. So CMS is here, and Atlas is on the other side, and you can see the Lake of Geneva here. And so it's a very small village. It's a very nice place. You need to drive a little bit from CERN to get there, but it's a very nice place to do shifts in particular. So you are very welcome to join CMS for this. But first, CMS is a great collaboration. It's a lot of people. You see that we have in total 6,000 collaborators, but in this 6,000 you really have 2,100 physicists, 1,200 doctoral students, 1,300 non-doctoral students, so lots of students, lots of physicists, and about 2,000 authors on the publications. To give you an idea, we have published about 1,400 scientific papers in peer-reviewed journals since the beginning of the LHC, so about 15 years ago, so it's about 100 papers published per year, and last year we published 110 papers. So it's really a lot of science coming out of this experiment. And of course, India is full part of it. India is an important part of CMS. It is the largest contributor in Asia. It's also the second largest contributor outside of Europe, after the US, which is a big part of CMS. So it's a great contribution, and you can see all the different institutes in India who are involved in CMS. Yeah, I just want to say also that the science production by Indian physicists is important, and there is this number here which shows that about 12% of all the CMS publications have at least one collaborator from India contributing. So this is CMS as seen from the transverse plane. So here the collision appears in the center. So you have to imagine that the beams are perpendicular to the screen. And it is called CMS because there is this huge magnet here, which is a solenoid. So that's the S of CMS is because of this magnet here. So the size of this magnet is 6 meters in diameter and 12 meters in length. So it's the largest supraconducting solenoid in the world. And the field inside the magnet is of the order of 4 Tesla. In fact, it's a little bit less, it's 3.8 Tesla. So CMS means compact muon solenoid for 3 reasons. First, because of the solenoid. 2, because it is compact. Compact means it's very small compared to Atlas, for instance, and very heavy, more than 14,000 tons. Sorry, 1,400 tons. So Atlas is much bigger. It's about the double in size, and much lighter. It's about twice the weight of CMS. So inside the magnet, you have a big field of 3.8 Tesla, and outside you have a smaller field. And here you can see a muon, which is a very penetrating particle, which can be measured both in the tracker detector here and in the muon chamber here. And that's why we call CMS this compact muon solenoid. But it's not only about detecting muons. We also have calorimeters. And here you have, for instance, the forward calorimeters, where there is an electromagnetic calorimeter and a hadronic calorimeter. So this is to measure all the neutral particles and the electrons in the electromagnetic calorimeter and in the hadron calorimeter. And you have also here, you can see muon chambers, which are used to detect muons in the forward regions. And some of these muon chambers are gem chambers. Some of them have been developed, in particular in India, and installed a few years ago. So these are some pictures of CMS. Here you have a picture of the central detector, which is made of silicon. As you can see, it's a full silicon detector. And here you can see also, it was also shown in the video, you can see also some of the crystals that are composing the electromagnetic calorimeter of CMS. And so this is a very pure, transparent, scintillating material, extremely heavy, made of lead tungstate. And this is a perfect material to be extremely precise in the measurement of photons and electrons. So this is a reconstruction of an event in CMS. So you have to imagine, what you see in blue here is in fact the shadow of the electromagnetic calorimeter. So this is composed of 1,000 of these crystals that we just saw. So these kind of crystals, in total, there are 70,000 crystals in the electromagnetic calorimeter of CMS. And here what you can see is the shadow of these crystals, right? So this size is about, from here to here, it's about 1.2 meters, right? So the total is about 3 meters. The collisions happen exactly in the center of the detector here. And what you can see here are the tracks that are produced in the collision and that are reconstructed thanks to the tracker. And what you can see in green here is a large deposit, two large deposits of energy in the electromagnetic calorimeter. And this is the sign of photons because there are no tracks associated to them. So you have two very energetic photons. And if you compute the invariant mass using the formula E2 equals P2 plus M2, you will find, you can determine the mass of these two photons, the invariant mass of these two photons. And this particular event is consistent with the Higgs boson decaying into two photons. It is not necessarily an Higgs boson, it can be a background event, as you can see on this plot, for instance, is that there are lots of events with two photons which are not at the mass of the Higgs boson, but the Higgs boson is here. But if you remove the background from this plot here, you would have a very nice signal of a Higgs boson. So here there are four different representations because I want to illustrate the four possible production of the Higgs boson, the main production of the Higgs boson at the LHC. The main one is what we call the gluon fusion, where two gluons enter in collision through a loop of top quarks to produce a Higgs boson. And this is really the major production of the Higgs boson, 86%. There is another one which, with the two gluons in the initial state, where the Higgs boson is produced with two top quarks. So this one is very rare, it's less than 1%, but you can see that there are less backgrounds and you can have a very convincing signal. And the other two are with initial states with quarks and anti-quarks colliding and producing also jets in the forward and backward regions. This is called the vector boson fusion production. And this one is called the production in association with a vector boson. So this is an example where the Higgs boson candidate decays into 4 leptons. So you can see 2 electrons here. So you can see the tracks here in the tracker and the deposit in the calorimeter. Here the second electron. And here you can see 2 muons in red, where you have also a signal in the muon chambers. So this is an event with 4 leptons, 2 electrons and 2 muons. And if you take this example here, you have a candidate Higgs boson which decays into 2 muons. So this is an extremely rare decay of the Higgs boson. When we put all the data together, all the information that we have about the Higgs boson, we can produce this plot, which in some sense completely summarize the interactions of the Higgs boson with the other fundamental particles. So in this plot, as usual, this is a logarithmic scale on the x and y axis. Here, this is the mass of the particles from the muon to the top quark. And here, this is the strength of the interaction of the Higgs boson with those particles. And you can see that the strength follows this, slope here, which is the prediction of the standard model. And as I told you, from the beginning, this prediction was a very solid prediction for the Higgs boson. And it is completely demonstrated by ATLAS and CMS. And this proves that the boson that was discovered is indeed, has indeed all the properties that were expected from the Higgs boson of the theory. So this is a striking confirmation of a prediction that originates from the first theoretical work by several groups in the early 64 for the first papers. And that's why the Nobel Prize was awarded to two of these persons, two different groups, François Englert and Peter Higgs, for the theoretical discovery of a mechanism that contributes to the understanding of the origin of particle mass, and which was recently confirmed by the discovery of the predicted fundamental particle by the ATLAS and CMS experiment at the CERN LHC. So this is a great achievement, I think, for CERN and also for the two experiments. The fact that the experiments are actually cited in the Nobel Prize award is really important for us. So now we can measure the mass of the Higgs boson very precisely, and this is done in this 4-lepton final state. Here you see the peak of the Z boson, a very rare decay of the Z boson at 91 GeV into 4 leptons, and here you can see the Higgs boson into 4 leptons, exactly at 125, with an uncertainty which is of 120 MeV, which corresponds to 0.28%. So this particle, which was discovered less than 14 years ago, is now known with an extreme precision, thanks to all the work that has been done by ATLAS and CMS during this last 14 years. Here you have a measurement of the top quark mass, which is the heaviest particle of the standard model, and you see that it's around 172 GeV, with a precision which is of 350 GeV, which corresponds to 0.2%. It's a little bit less good than for the Higgs boson, but it's much more difficult to measure the mass of the top quark. And if you are interested, there is a review that we have published last year on the various ways we can measure the mass of the top quark. So why is this important? Because the mass of the Higgs boson and the top quark are driving the stability of the universe in some sense, because if you look here at the Higgs potential that I showed before, it depends on one parameter which varies as a function of energy. So this parameter depends on the mass of the Higgs boson and the mass of the top quark. And depending on the way this parameter varies, then the Higgs potential can have different shapes at very high energy. When this lambda parameter goes to 0 and becomes negative, then the potential will come to a maximum and then start to decrease. And then this minimum will not be a minimum anymore, and the universe is not stable anymore, right? Now, what we call metastable, it depends on the possibility of the actual electroweak minimum to tunnel through quantum effect to the new minimum. And if this time, the characteristic time of this transition is larger than the edge of the universe, typically, several billion years, then we say that it is metastable. We can also translate that into energies. What we know from this measurement here is that the top mass is here and the Higgs mass is here. So the universe is here, which is just at the limit between a region of stability and a region of metastability. It's on the metastability size, but it is the characteristic time is so huge that in fact we can consider that the universe is stable. What it means is that the standard model from which these measurements, for which this result was derived, could be valid up to phenomenal energy of the order of 10 to the 11 GeV. There is no reason why we could not keep the standard model as the good theory for all the processes up to these absolutely mind-blowing energies, right? But we have other problems which let us think that the standard model is not the end of the game and that there are probably new phenomena beyond the standard model. Some of them are of theoretical aspect. One of them is what we call naturalness. It's just the mass of the Higgs boson is so small that you need to have a very strong fine tuning in order to cancel all the quantum corrections that tend to send the mass of the Higgs boson to the highest energy. So this is the fine tuning problem, which is really a theoretical problem. Then another one is ground unification. If you take the standard model as it is, then the ground unification almost happens, but not quite. So if you want the ground unification to happen at 10 to the 15 GeV, then you need to add a little bit of new physics. There are other problems that I don't have time to talk about, but now what I want to talk about is another test of the standard model, which involves the measurements of the W boson. So to measure the W boson mass, which is one of the most complicated, difficult, and challenging measurements at the LHC and in other experiments, you need to select W boson event. The problem is that the W decays with the neutrino in the final state, which is not seen. So what you select are events where there is only one muon and missing energy, as in this particular event. What we have done is to select 100 million of such events, and we have analyzed these events together with a smaller sample of Z events decaying to 2 muons. So you can see here the signal of the transverse momentum of the lepton of the muon here for the W sample, and here you can see the invariant mass of the 2 muons for the Z sample. And from these distributions, with a lot of work and a lot of understanding and calibration of these objects, the muons in particular, you can measure the mass of the W and the Z boson, in particular the mass of the W, with an incredible precision. Here it's a precision of less than 10 MeV for a mass which is of the order of 80 GeV. So it's a precision of 0.012% on the mass of the W boson. Right? What you can see is that our measurement is not only the best or almost the best measurement, it is in agreement with other measurements at the LHC and other experiments. And it's also in agreement with what we call the electroweak fit. And this electroweak fit involves all the measurements that have been done, in particular at LEP, the electroweak measurements, precision measurements, but also the measurement of the top quark, which is done at CMS. And you see that the top quark at CMS selects this region, which is a little bit below the measurement of CMS, and corresponds to this gray band here. So this shows that the CMS data are consistent. The measurement of the W mass, the measurement of the top quark mass, and the measurement of this parameter, which is the ratio of the weak force to the electromagnetic force, those three measurements are in extremely good agreement, and this is a non-trivial test of what we call the gauge sector of the theory. This test proves that there is no new physics, in particular in this area, which is something which is extremely important, but the next generation of accelerators will try to even improve this kind of test. So we have seen that the standard model was extremely solid. It seems to be stable until very high energy. It passes all the tests that we are trying to do, but still we believe that new physics is necessary. And why? And here it's a list of some of the reasons. The fact that neutrinos have mass, implies that the standard model as it is now needs to be modified. There is the existence of dark matter. I will come back to that. There is also the existence of the baryonic asymmetry, which is the fact that the universe is made of matter and not antimatter. And this was also the question that you asked. This is a very important thing, which is the acceleration of the expansion of the universe. So for this, I need to go to this plot here, where you see here the Big Bang and here today. So the time goes from left to right on this plot. And what you see here is the rate of the extension of the expansion of the universe. So the rate of expansion of the universe decreased a long time ago, more than 10 billion years ago, because the universe was dominated by matter. In fact, it was dominated by dark matter. So this is a dark matter dominated universe here, a long time ago, but about 5 billion years ago, things changed. And all of a sudden, the rate of expansion of the universe started to speed up again. So there is a change between slowing down and speeding up again. So this is really the effect of normal matter. Gravitation opposes to the expansion. And then there is a force which is trying to accelerate the expansion. And this is one of the most important discoveries, I think, in the past 20 years. It's the fact that the universe is actually, expansion is actually accelerating. And thanks to this, we know now that a large part of the energy of the universe is not only in the matter, the ordinary matter and the dark matter, but also in this important part, which is what we call dark energy. Right? So if you look at these plots, you see that dark matter and dark energy, 35%, 25%, 70%, are of the same order. And this is a very unusual case where, because if you look at the previous representation, in the past, it was 100% dominated by matter. In the future, it will be 100% dominated by dark energy. And we are just in the middle where dark matter and dark energy are almost balanced. It is a very non-usual and unique time in the time of the universe. So dark matter, we know that it exists at all scales. It exists it is seen in the rotation curves of the spiral galaxies. It is seen at the level of the galaxy clusters. It is seen at a much higher level to explain the cosmic web of the distribution of matter and structures in the universe. And it is also seen in the anisotropy of the cosmic microwave background. So we know that dark matter exists. If dark matter is made of heavy particles which interact weakly with the standard model particle, then it can be produced at the LHC. You see, if there is an interaction whatsoever between dark matter particles and the standard model, then two standard model particles can produce two dark matter particles. Right. So this is a very small assumption that there is some interaction between dark matter and standard model particles. But we expect that if they exist, it should be seen in ATLAS and CMS and other experiments. So we are trying really an extensive program to search for dark matter. And as you can see, we are going in all the possible directions that we can think of, either looking at extended dark sectors, including supersymmetry that you have probably heard about. So we are trying to look at signature of supersymmetry, including finding supersymmetric particles. And then more recently, we developed this idea of simplified dark sectors where we consider that the dark sector can be reached using portal particles. And these portal particles can be either scalars or vectors. And in the scalars, of course, you have the Higgs boson, which could be a portal to the dark matter. And so we have tried all these possibilities. So you can see here various analyses in CMS putting limits and not finding any of these signals. There is a very nice review of all the different searches for dark matter. So far, we have not found any dark matter in our data, and we have not found any new physics in our data. So where are we today? So today in 2025, we are here, in the middle of what we call the run 3. Most of what I've shown today was based on the run 2 data, and the Higgs discovery was at the very end of the run 1 data. So we are here today, and we have still 1 year and a half of data for run 3, and then there will be this long shutdown of 4 years in which the machine and the experiments are going to be upgraded for the high luminosity phase of the LHC that you can see here, where we will go from 500 inverse femtobarns, which is what we use to measure the amount of data, to up to 3,000 inverse femtobarn. So we will multiply in 10 years sixfold the data that we'll have at the end of run 3. So it's a huge amount of data, and it's a huge amount of intensity as well. So we need to have a better detector to take this challenge of the high luminosity LHC. Here you can see the various improvements that we are going to bring to CMS with several technological challenges that we are implementing and several paradigm shifts, in particular the track trigger at level 1 trigger, the particle flow and machine learning also at level 1 trigger, an imaging calorimetry, extremely granular calorimetry, and introducing a 5th dimension in the measurement of calorimetry with precision timing. In this endeavor, India has really an important role. India is contributing in the CMS upgrades in several aspects, but very important one, the outer tracker, which is really the heart of the experiment. The trigger, as I say, which will be extremely important because it includes this track trigger in particular. The GEM muon detectors, which are those detectors that I showed you previously, which will help in triggering muons in the forward regions, and the very high granularity calorimeter, the HTCal, where also India is participating in particular with a MAC, Module Assembly Center in TIFR. So here, just to show you the example of what will be possible in CMS at level 1 trigger. So it's really online. You will have tracks for the first time in particle physics. We will have also the detailed information from the high granularity calorimeter, as you can see here. So it will be really a great improvement compared to even what we have today. So I come to my summary. I think that the discovery of the Higgs boson by Atlas and CMS is the confirmation of a great adventure, a theoretical adventure, because it was a prediction of the theory, but also an experimental one. I did myself my thesis in the 90s searching for the Higgs boson at LEP, so it's something that some of us have spent a lot of time, and finally we found it. It consolidates the standard model of particle physics and also shed light of one of the important epochs of the history of the universe, 10 to the minus 11, 10 to the minus 12 seconds after the Big Bang. It's the farther that we can go with particle physics. And it explains also how matter, as we know it, came into being, and in particular, all the implication that it has for the fact that we are here talking about it today. So CMS continues to explore the LHC data. We are all looking for new physics, either by doing precision physics or by searching for new phenomena or new particles. But everything is based on the fact that we want to find a breach in the standard model and find new phenomena. Much more data is needed to progress on the fundamental questions. We talked a little bit before about the matter-antimatter asymmetry. It turns out that in the standard model, the electroweak transition is a second order transition. It's a smooth transition. If you want to have the standard model explaining this asymmetry, you would have to have a first order transition, like the potential that is shown in red here. So this is an alternate potential with new physics, which can give you a first order transition between at the electroweak transition. And if you want to distinguish between those two models, you need to measure the shape of the Higgs potential very precisely, and this will be possible thanks to the HL-LHC data. Okay, and finally, if we want to be able to take this challenge of this huge amount of data at HL-LHC we need to have a much better CMS, a high luminosity CMS if you want, and we are engaged in a very ambitious and innovative program to upgrade the CMS detector. So to finish, I just want to say that in April of 2019, in my hometown of Paris in France, there was this terrible event of the main cathedral of the city, Notre Dame, in fire. I don't know if you've heard about it, maybe. So it was 5 years ago, and you see here just the moment where the flesh fall into the transept and broke completely all the internals of it was a terrible moment when this fall into the cathedral. Everybody thought that the cathedral would collapse and would be destroyed. It was not completely destroyed. And 5 years and a half later, in December of last year, it was reopened, completely rebuilt, and as new. And now you have the Notre Dame in Paris, which is as beautiful as ever. This has been done in 5 years, a little bit more than 5 years. It has taken about 2,000 people to rebuild this cathedral. And 5 years and 2,000 people is what we have in CMS to actually build the upgraded CMS for the HLLHC, so I think we can do it.
Thank you for these very insightful talks. We can take some questions from the audience. Yes.
Yeah, thank you for this talk. So that curve we are seeing, that V5 versus phi, I don't know what exactly the phi is, but is there any meaning of the negative side of the phi? So is there any negative phi there is a minima in this curve?
So phi, it's simplified, right? So phi is supposed to represent the X field.
Huh.
The X field is a scalar field, but it has 4 degrees of freedom.
Okay.
What should be shown here actually is the average of this field.
Oh, okay.
Okay, so this in fact represents energy. The x-axis represents energy.
So only absolute value matters here.
This is in fact the energy density of the X field in the vacuum, which we call the X condensate.
Okay.
Right? So the shape of this potential depends on a certain number of parameters in the standard model. And in the standard model, the parameters are what we call running, so they depend on different other parameters of the standard model. So you can calculate the way the parameters vary as a function of energy using theory, using quantum theory, and you can do it at several orders of quantum theory. So the calculations are sometimes very difficult, so that's why there are uncertainty even in the calculations. But then by doing these calculations, you can actually measure, you can actually predict how this potential is going to evolve as a function of energy. It was your question? Or?
Yeah, my exact question was, is there any meaning of a negative of the phi? Like say, in the negative side, if I extend this curve.
Sorry. No, you need to imagine that the potential is symmetric with respect to the vertical axis.
Okay. It is just a projection.
Yeah. So it is symmetric with respect to the vertical axis. So that's why it has this. What we so often show it as a Mexican hat, because you need to imagine that it is completely symmetric. So I just showed a part of it.
Okay. Thanks.
So it goes also on the negative side. Yes.
Okay. I had another question. Can I go ahead? Huh? Oh yes.
Thank you for a real nice talk. Would you like to talk something about primordial monopoles regarding the experiments or efforts in discovery?
So primordial monopoles is also a big mystery. They should exist. There is no reason why monopoles would not. So you're talking about magnetic monopoles?
Right.
Yes. So in principle, these objects should exist, and they could have been produced in the very early universe when the universe was extremely hot, and there are several conditions under which some of these could have been stable enough to continue to be to be detected in the universe, but they are none detected in the universe. So what we do at the LHC is we are trying to look for magnetic monopoles which are produced in proton-proton collision. So there are certain theories in which this is possible, but this theory involves new physics such as extra spatial dimensions. So they are quite exotic theories, but so we are still trying to look at them. In principle, it should be extremely difficult in the framework of standard physics. It's very difficult to produce magnetic monopoles in proton-proton collision at this energy. You need to really inject exotic physics in order to. It's like black holes. If you want to produce black holes in proton-proton collision, you need somehow to change something in gravitation. So by, for instance, introducing new dimensions, because otherwise the gravitational interaction is too small to produce black holes in proton-proton collisions.
Yes, Professor.
Yeah. What is the highest energy you're expecting to reach at the HLLC, and what are the plans for the energy frontier?
So at the HLLHC, so now we are running at 13.6 TeV. The nominal energy of the LHC is 14 TeV. When you discuss to the machine people, they think it's already very challenging to go at 14 TeV. So chances is that we are going to take data at 13.6 TeV, at least for run 4, and maybe later we will try to go at 14 TeV, but we don't expect to go much higher. So HLHC is not going to run at higher energy, but at much higher intensity. Right? So instead of having, say, 60 simultaneous collision per bunch crossing, it will go up to 200. So there is much more intensity in the beams and in the, so then there is a discussion now in the world and also in Europe about the next machine. So if you want to go at higher energy, you need to have also a hadron machine. And the only projects of hadron machine at higher energy are either the FCC-HH at CERN, which would be the machine which will succeed after the FCC-EE. And there is also a project in China which will be the same after the CEPC, which is the E plus E minus X factory, in the project of E plus E minus X factory in China. Now, you could also imagine that if either the FCC or the CEPC are built, to reuse the ring of the LHC and to put in better, stronger magnets if they exist and when they come. And then you can imagine that, but the limitation here will be something like 30 TeV and not more than that. If you manage to double the field, the BDL of the magnets in the LHC tunnel. That would be the limitation.
So thank you. We have to stop here.
Actually, I do have one question. Sorry.
Okay,
It's
last one.
me.
Okay, quick one, please.
What my question is, does dark matter interact with the X field? If not, is there
Can
any...
you please be a little louder? Yeah.
I'm audible? Okay.
A little more.
Okay. Does dark matter interact with the X field? If not, is there any dark Higgs according to supersymmetry model?
Yeah. So yeah, there are models where. So if you look here, for instance, where in the standard model there is no dark matter, right? In supersymmetry there is dark matter, and this dark matter may, in some cases, interact with the X field, because this dark matter is, if you look into the most popular SUSY breaking models, there are cases where there are interactions between dark matter, which is the neutralino, and the X field. What we do in simplified dark sectors is to imagine that the Higgs field can be a portal to the dark sector. And so in this theory, we assume that there is a connection between the Higgs field and the dark matter. This is the assumption. So this is really what's behind those spin zero portal models that are here. But this is a class of models, and there are other classes of models where the Higgs field is not and the dark matter do not interact. Now, the good question is about, so this is a good question, but the good question is, do neutrinos interact with the Higgs field? Because we know that neutrinos have mass, and we have seen that the leptons got mass by interacting with the Higgs field. What about neutrinos? And this we are not sure. That's why the neutrino physics is so exciting. I believe that neutrinos are Majorana particles, and that part of the mass of Majorana particles comes from the Higgs mechanism. So there is a little bit of Higgs mechanism, but not only, and there is another mechanism that we call the CISO mechanism, which involves new physics at higher energy. And that's why it's very exciting at the LHC to look for heavy neutral leptons, which could be the sign of this mechanism and explain partly how neutrinos get mass. And what's the fraction of the mass that comes from the Higgs mechanism and the fraction of the mass that comes from the CISO mechanism.
Thank you. Let's thank Professor.
Unnecessary Nagaraja idol and footnote. Lord Shiva's cosmic dance. Unnecessary dispute. It is unscientific.
What?
Summary. Slide. Nagaraja picture is unnecessary.
Lord Shiva's cosmic
Lord
dance.
Shiva's cosmic dance. It is unnecessary. It is unscientific.
We should stop here. Yeah, okay.
What are you doing? You are doing unscientific.
Let's thank Professor Gautier.
Is it wrong or is it unethical?
I think it's a bit religious.
Because, sorry, so this statue is at CERN. What you see here is building 40. And this building is where we have our offices. Atlas and CMS are hosted in these buildings. And here the building is building 39, where there is the CERN hostel. And between the two, there is this statue. This is not a statement, a religious statement. It's just a statue that exists at CERN. The footnote is a link. If you click on it, it's a link which shows the inauguration of this statue, where the Director General of the time, Robert Aymar, was received this. Okay. No problem. It was a gift from India. Yes.
Yeah. Which we thanks.
Okay, let me thank all the speakers for the beautiful talk on the sun, as well as Indians' contribution, as well as how it has evolved in the last 70 years and what will be happening next 70 years also. It's very informative, and I would like to thank all the speakers and all of you and making this event grand successful. At this occasion, I would request Dr. Ipsita to do the vote of thanks.
So it's a privilege to stand here and express my heartfelt gratitude on behalf of all of us. First and foremost, I would like to extend my sincere thanks to the director of our institute, Professor V. Kamakoti, for his continuous support and encouragement. I would like to express our deepest appreciation to our sponsor, ICSR IITM. The Dean of ICSR, Professor Santanam, graced the stage at the beginning. I would like to thank all our respected chief guests for taking the time to join us today and sharing your inspiring thoughts. Your presence has truly made this occasion special. Very special thanks to all the speakers of these sessions for taking the time to give all this fascinating and insightful information, and be patient with the questions and answering nicely. I would like to thank all the organizing team. So, Department of Physics IITM is a part of the organizing team, and particularly Professor Behera took the lead in organizing this event. So, thanks to him. I'd like to extend my gratitude to all the volunteers, student volunteers. Many of the student volunteers came forward. Without their hard work and effort, this event would not have been possible. So we should really thank them. I could not name them because there's quite a few number of students who helped. So, and finally, thanks to all the participants for being here and supporting us. Your presence means a lot to us. So thank you all. Have a very wonderful evening ahead.
So there is a high tea outside. Please help yourself. I would like to invite all the volunteers to take a photo with our delegates.